All right, let's dive into a tool that, I'm not gonna lie, can look pretty intimidating to engineering students, but it's absolutely fundamental to how we build our modern world. I'm talking about thermodynamic property tables. We're gonna demystify them right here, right now.
And this quote just hits the nail on the head. You know, these tables might look like a phone book full of random numbers, but they are the bedrock of thermal design. So try to think of them less like a spreadsheet and more like a treasure map, a map that charts the very existence of a substance as it flips from liquid to gas and back again.
So, why do we even need this map? Why can't we just use a nice, neat equation? Well, the truth is, those elegant formulas we all learn in basic physics, like the good old ideal gas law, they're just that, ideal. They work great for simple gases, but the second a substance does something interesting, like water boiling into steam, those simple equations completely fall apart.
So here's our itinerary for this journey. We're going to see exactly why equations just aren't enough. We'll map out the super important vapor dome, learn to navigate its three main zones, get a handle on this idea of quality, learn how to read between the lines, and then finally, see how to use this knowledge like an engineer's secret weapon.
First things first, let's really dig into why simple math just doesn't cut it for this kind of work.
You know, the ideal gas law is based on this kind of charming but totally false idea that gas molecules are just these tiny little dots bouncing around that don't interact. But in reality, especially in something like steam, molecules get crowded. They push, they pull, they attract and repel each other. And during a phase change, like boiling, those interactions are everything. And the ideal gas law just becomes completely irrelevant. That's why we need real, measured empirical data.
So, to measure just how far off we are, engineers use something called the compressibility factor, or Z. Now, for a perfect, theoretical, ideal gas, Z is always exactly 1. But for a real substance like steam, Z is all over the place, depending on the pressure and temperature. So in a way, you can think of the property tables as just a giant record of Z's behavior, showing us exactly when we can get away with a simple equation and when we have to pull out our detailed map.
So what does this map actually look like? Well, let's explore its most famous landmark, the vapor dome.
On the left-hand side of this dome, we have what's called the saturated liquid line. This is water at its boiling point. It is right on the hairy edge of turning into steam. In the tables, we use a little subscript F, which stands for fluid, to mark any property in this state. You add one more little bit of heat and boom, it starts to boil.
Now, on the right boundary of the dome, we have the saturated vapor line. This is the exact moment when the very last drop of liquid has just finished turning into vapor. It's just pure steam, but it's teetering on the edge of condensing. For these properties, we use the subscript G for gas. Take away just a tiny bit of heat, and it starts turning right back into liquid.
And right at the very peak of the dome, well, that's where things get really, really weird. This is the critical point. As you keep cranking up the pressure and temperature, the liquid expands and the vapor gets more compressed, until, at this one single point, they become completely identical. You can't tell them apart. The whole concept of liquid or gas just dissolves into this single bizarre state called the supercritical fluid.
Okay, so we've got our map laid out. Now let's figure out how to find our exact location on it. The rule is actually pretty simple. We just need two independent properties, like temperature and pressure, and we can figure out everything else.
And that leads us to the most fundamental question for any engineer. You look at your gauges, and they show a certain temperature and a certain pressure. So what's actually going on inside the pipe or the tank? Is it liquid, is it gas, or is it some messy mixture of both? Well, the tables give us a crystal clear answer. You just look up the saturation or boiling temperature for the pressure you're at. If your actual temperature is lower than that, you've got a compressed liquid, basically think of regular water. If your temp is higher, you have a superheated vapor, that's dry and visible steam. And if your readings match the table's saturation values exactly, well then you are inside the dome in a saturated mixture of both liquid and vapor.
So let's talk about that most interesting place, inside the dome. How in the world do we describe something that's part liquid and part vapor at the same time?
We use a special property called quality, and we give it the symbol X. It's way simpler than it sounds. It's just a percentage of the mass that's in the vapor phase. That's it. So a quality of 0, or X equals 0, means you have 0% vapor. You're a saturated liquid on the left side of the dome. A quality of 1 means you have 100% vapor. You're a saturated vapor on the right side. And a quality of, say, 0.25, it just means 25% of your mixture's mass is steam.
And this idea of quality gives us an incredibly powerful tool.
It basically works like a slider to find the average properties of our mixture. We start with the property for the pure liquid, that's YF, and then we add a fraction of the difference between the vapor and liquid properties. And what's that fraction? It's our quality, X. This lets us calculate any property we want, like specific volume or total energy, which we call enthalpy, for any point inside that dome.
Okay, but let's be real. What happens when the exact temperature or pressure you're working with isn't actually listed in the table? This happens all the time. The answer is, we have to learn how to read between the lines using a simple math trick called interpolation.
So, for example, let's say we need to find the specific volume of steam at exactly 155 degrees Celsius. We open our steam table, and we only see values for 150 and 160. We're stuck in the middle. We know the answer has to be somewhere between 0.39 and 0.30, but how do we get the exact number?
We use a really straightforward technique called linear interpolation. Don't let the name scare you. Since 155 is exactly halfway between 150 and 160, right? We can just assume that the specific volume is also going to be exactly halfway between its two corresponding values. We're really just finding the average of those two numbers. All we're doing is drawing a straight line between the two data points we do know and finding our value along that line.
So we've got all these tools. We can read the map, we can navigate the zones, we can even read between the lines. So how do engineers actually use this stuff? This is where our theoretical map becomes the actual blueprint for the modern world.
Think about a power plant. Engineers use these tables to trace the path of steam as it blasts through a turbine. If they get it wrong and water droplets form inside, those droplets act like microscopic bullets that will literally shred the turbine blades to pieces. Or, in your refrigerator, these tables map the journey of refrigerant as it expands and gets cold. The data in these tables is so rich, you can even use it to derive other crazy physical properties, like the speed of sound in steam.
So if you take one thing away from this, let it be this. These tables are so much more than just data. They are the essential bridge that connects the abstract laws of thermodynamics to the real-world machines that power our entire civilization. They translate physics into the language of engineering.
And, that brings us to a final bigger thought. The journey across that vapor dome shows us that liquid and gas aren't really two separate things. They're just two faces of a single fluid state. So it kind of makes you wonder, doesn't it? What other concepts in science that we treat as totally distinct might actually just be different perspectives of a single, deeper truth?